So in this video we're going to continue our discussion of circuits that have any kind of element we want, capacitors, inductors, and resistors. In the previous video we found the solution of the circuit when the source was a complex exponential. Well, that's a mathematical toy. We can't really produce sources that look like that in the lab or in the real world. So is that just a mathematical thing that's kind of fun to play with? Well, it turns out it's much more important than that. We're going to see how we'll apply that knowledge we developed last time when the source is a sinusoid. Turns out it's an easy extension of what we already have done. So let's review very quickly the way the so-called impedance method works. We start with our circuit. We pretend the source is a complex exponential, and that means we can now only worry about complex amplitudes. We replace every element by its appropriate impedance, whatever it may be, and then we can use what we learned from resistive circuits, voltage divider, current divider, series parallel relations, to figure out how the output variable's complex amplitude is related to the complex amplitude of the source. Okay, so that's what we learned last time, except now we want to handle a bit more real-world sources than complex exponentials. So what we did is we applied it to our simple RC circuit. We replaced it by, thought about it as an impedance kind of circuit. And I want to make sure we note that this is a lowercase v in over here. It's supposed to be v in of t. This is lowercase v out of t. But over here we're only talking about the complex amplitude. So I'm thinking about this as being a complex exponential source. And now everything in this circuit is a complex amplitude. And what we discovered when we used our voltage divider for this circuit was that the amplitude of the source, amplitude of the output rather, was equal to this quantity times the amplitude of the input, and I'm uncanceling the complex exponential so we get the entire answer. Okay, so that's what happens when the source is a complex exponential. Well, what I want to now do is talk about the case where the source is a sinusoid. This sinusoid has a frequency f0, and it has an amplitude of a. Okay, well, that's not the same as a complex exponential. So how does this result apply to the case where that's what the source really is? Well, the mathematical trick is Euler's formula. We know from Euler's formula that a cosine is equal to 1/2 times e to the j theta plus e to the minus j theta. A complex exponential rather at an angle of theta, and a complex exponential at an angle of minus theta. That's a cosine. So that applies to the case where we have theta here is just cosine 2 pi f naught t. So I think of this as being a positive frequency complex exponential, and this being a negative frequency complex exponential. This may sound a little strange, negative frequency things, but it turns out this is really very important and the right way to think about it. So we can figure out what the output is for each piece at least. We know that if the source was this term, that's the output. And we know that if it's the negative frequency term, all we have to do is replace f by minus f, and we get the answer. So we know about each piece of the original cosine. We know what the output is for each of those. But how about putting them together? How do we do that? Well, now we get to the really interesting conclusion. Now, so this is where we are. We use the complex exponential source to hop over to the impedance version, use all the tricks we've learned for resistive circuits, and now when the source is a cosine, I want to point out that all the circuit elements we've been talking about, resistors, capacitors, inductors, and the interconnection laws, KVL and KCL, are linear, which means superposition applies. Remember what the definition of linear was. That if the input consists of a sum of terms, the output also consists of the sum of the outputs to each term considered separately, and you just add them up and multiply by a constant if there are any output. So, we're done. Based on what we already know, we know that the output voltage, and notice this is lowercase v, is the output to the first term plus the output to the second term, added up, and since there's a weighting factor of 1/2, it goes there too. And this is because of superposition, because the circuit elements we've been talking about are linear. This is why the linear concept is so important. It really makes our life easy. Okay, so let's continue this. I'm going to show you how to simplify that answer. It looks a little daunting as it stands right now, but there's another mathematical thing we can do. Now, so this is Euler's formula for the cosine, and the source was 2 pi f naught t. And like I said, I thought about this as a positive frequency term and a negative frequency term. Well, there's another way of thinking about this. Suppose this is a complex number z. This is z conjugate. I'm adding them up and dividing by 2. Well, that's the formula for the real part. And so we're actually writing the source as the real part of a complex exponential. Well, the output looks very similar, right? There's the positive frequency term, there's the negative frequency term, but that still is something plus its complex conjugate divided by 2. That's the real part. So this, if you will, is the trick. We can think about when we have a source that is a sinusoid, you can think about it as the real part of a complex exponential. The output is going to be the real part of the same complex exponential with the amplitude modified by what the circuit does that we found using voltage divider. Well, how do you find this real part? Well, mathematically, we have a situation where we have something in Cartesian form and something in polar form. And we need to figure out how that real part the easiest possible way. And their answer is to convert the Cartesian form to polar form. So that's what I've done. So this is the ratio of something in Cartesian coordinates, 1, and the denominator, j2 pi f naught rc plus 1. And as I showed you, the magnitude of a ratio is the ratio of the magnitudes. So 1 obviously has a magnitude of 1, and the magnitude at the bottom is the imaginary part squared plus the real part squared, and you take the square root of the result. Okay, that's where that comes from. The angle of a ratio is the angle of the numerator minus the angle of the denominator. And the angle of 1 is 0, and so what we're left with is that's the angle. Okay, so now we need to simplify further. All I'm going to do is merge the two complex exponential terms into one term because the exponents add. And now taking the real part is easy because this is just some real number so far as the mathematics is concerned. The only thing complex is this, and that's e to the j theta. And what's the real part of e to the j theta? That's just a cosine.